Hi everyone, at this point you should have the Lattice IceCube 2 tools installed, and hopefully you've gotten a little familiar with those. The other things you're going to need to download are the Lattice Diamond Programmer, the standalone programmer. You're going to need to download that for either Windows or for Linux, and you're going to need the virtual COM port drivers for the Go board, which are available on the FTDI website. I will link to both of those in the notes for this YouTube video, but you are going to need to download both of those so that you can both program the Go board and communicate with it. So now it's time to get cracking on our first project here. And the first project is going to be something pretty straightforward. We're going to be implementing a very simple project where when you push switch 1, this is a switch 1 here, we're going to have D1, which is an LED, illuminate. When you push switch 2, D2 illuminates, switch 3, D3, switch 4, D4. And so the question is, what does the FPGA code look like to get this to work correctly? So I'm going to be taking you through both the Verilog and the VHDL solutions and going through the entire flow of the build process. Now this flow is important to get down and to pay very close attention to exactly how this works, because it's a multi-stepped approach and it's not very intuitive. So I'll go through this once for this video, and for future videos I will expect that you will just know how to program, so how to build the FPGA image, and then also how to program it to the Go board. So this is definitely an important video. Like I said, the code itself is not very complicated, but it will exercise some basic functionality and take you through the process. So with that said, I'm going to get started with the Verilog coding section. If you want to learn VHDL, skip forward a little bit and I'll do VHDL next. Alright, so for the Verilog code, I'm going to be editing my code in Emacs. If you don't know what Emacs is, I don't recommend learning it because it's really weird. But if you want to use something like VI, you're welcome to use that. I'm not going to weigh in on the Emacs versus VI debate because everything it's been already said. Use whatever you like. That's my approach. If you have no idea what I'm talking about, if the words Emacs and VI mean nothing to you, go get Notepad++, like literally the plus sign. That is definitely the best, simplest text editor out there, and it gives you what you need, which is syntax highlighting. Syntax highlighting is critically important. So when you type a keyword like module, it turns a special color. Module, coincidentally enough, is the very first keyword that is most important in Verilog. It defines the module or the code that contains some functionality. So you have to give it a name. Let's give it a name like switches to LEDs. Now, first thing I should say about Verilog is that it is case sensitive. So switches to LEDs, capital LEDs, is different than switches to lowercase LEDs. Fun fact. So you need to be careful about that. And all the keywords are lowercase. So open parentheses means I'm going to start defining my inputs and outputs. So input is a reserved keyword in Verilog. It means that this signal that I'm naming now is going to be an input to the module. So I switch 1, and we're going to have a couple switches. So switches 1 through 4 are my inputs, and I'm going to be defining some outputs as well. So O, LED 1, and we're going to do LEDs 1 through 4 as well. One nice thing about Emacs too is that it does some alignments for you as well, which is kind of fun. So now I have defined my module. So I have 4 inputs, which, as you saw on my diagram here, are my switches, and I have 4 outputs, which are my LED drives. So that defines the module for the FPGA. Now, these names are actually important. You do need to name your inputs exactly this and your outputs exactly this, because these are actually tied to specific pins on the FPGA. So I switch 1 is actually going to be routed to a very specific pin, and if you don't give it the right name, then it's not going to know which pin to put it on. So we'll get to that later on, but let's just, for now, just know that those names are actually kind of important. So the next keyword here is assign. Assign is used to assign wires which I haven't explained what that is yet, but for now, let's just say that we can just assign the outputs to the inputs. So we're going to be assigning them like this. So what this means now is that when switch 1 changes, it's going to be immediately assigned to OLED1, which is an output. So what this essentially is going to be doing inside your FPGA is it's going to be creating a wire, physical, real wire, between whatever pin switch 1 comes in on and whatever pin OLED1 goes out to. Kind of cool. So remember that when you're designing an FPGA, you're actually designing real wires, and you're designing real circuitry on your FPGA. And the last keyword here for this project is end module. And you're done. That's it. Save this file as switches to LEDs.v, for example. .v is a Verilog file. And that concludes the Verilog section. Alright, let's introduce the VHDL code for this project 1 here. I'm going to be using Emacs as my text editor. You are free to use whatever text editor you're most comfortable with. If you want to use VI, use VI. If you want to use Emacs, use Emacs. I have no preference between the two. I just learned Emacs first, so that's what I use. If you don't know what Emacs or VI are, if those words mean nothing to you, go download Notepad++. It's a really nice text editor that gives you syntax highlighting, which is important when you're writing code, because I don't know how anybody writes any code without some good syntax highlighting. So let's get into the VHDL code. The very first 2 lines you're going to need are going to mean nothing to you. They look like this. Library IEEE use IEEE.standard logic 1164.all. One nice thing about Emacs is that it has some built-in VHDL completion for you, so I didn't type all that, but Emacs is smart, knows what I'm doing, so it fills stuff in for me. So these 2 lines are important, and it's not exactly clear why at this point, why they're important, so let's just ignore them. I'm just not even talk about them right now. You need them, put them there. Don't question it. Next, entity. Give the entity a name. Let's just do this. Switches to LEDs is. So entity is it is the map. It defines the interfaces to this particular module. So we're creating the entity at this level here, which is around the FPGA itself. So we're going to have 4 inputs, which are your switches, and 4 outputs, which are your LEDs. So that's what the entity consists of. So the next keyword is port. Port, and that's going to be, so we're defining the port map for this particular entity. This is the words. And we need the name first, colon, direction, so in this case it's an input, space, and then the type. So in this case, standard logic. Standard logic is going to be the type. Standard logic and standard logic vector are the 2 most prominent types in VHDL, especially for port maps. I'm not going to talk about what it is, but for now just consider iSwitch 1 as a bit, so it can be a 0 or a 1. Okay, we're going to be we need the other ones too. So switch 1, 2, 3, and 4. 4 inputs, and we need 4 outputs as well. OLED1, colon, direction. In this case, it's an output, and it's the same type, standard logic. Let's get 4 of those bad Larrys. Okay, so each line is terminated with a semicolon, with the exception of the last one, because let's confuse you. You need a parentheses to close the port, and then you need a semicolon after it. VHDL, you will find, is very particular about syntax, so it does take some getting used to. Emacs, like I say, has some nice, it's got some code completion built into it, so it tells you if you're making a mistake when you're writing the code, but that's what a good compiler is for too, so you'll catch the error sooner or later, and it's just something to get used to. So you need to write end entity switches to LEDs semicolon. So this is the entity. We're done with that. A couple things about VHDL. Keywords, actually all of VHDL is not case sensitive. So OLED4 is the same as OLED1. LED lowercase 4. So that's different from Verilog, where Verilog is case sensitive. So you don't need to be super careful when you do that. But these names are actually important. iSwitch1, OLED1. Usually you can create your own names for the port map, except for the port map on the top level of the FPGA. And that's because you'll find this when we go through the build process, but iSwitch1 is actually a physical pin that on your FPGA. So the name is actually important. When the tools go to build the FPGA, it needs to see this exact name to know which pin to put it on. So next, we're going to be defining the architecture. VHDL has this notion of entities and architectures. Entities are kind of like your interfaces, and the architecture is what goes inside of it. They're more flexible than that, but I've never really used them in any other way other than that. So they're a pair for all intents and purposes. So let's write architecture. How do you spell that? Like that. You can give it a name. You can give it whatever name you want. I'm going to call it RTL, which stands for Register Transfer Logic. It doesn't matter what you call it. And again, Emacs populates some things for me. So the architecture, give it a name of entity name. This needs to match the entity that we defined earlier. Is, and then there's some space here, and then the keyword begin. And then inside the begin is where the architecture can actually exist here. And then we have at the bottom end architecture name. And inside the architecture, this is going to be pretty straightforward. We're just going to be assigning the outputs to the inputs. Now this may look a little strange to you, because who has ever seen a less than, this looks like less than or equal to or something like that. This is actually the assignment operator in VHDL. That's what it's called. It's a less than sign with an equal sign after it. So what this means is that when the value of iSwitch1 changes from a 0 to a 1, the output OLED1 will immediately change as well. So what this is going to happen is that we're actually going to be creating a wire from this pin, OLED1, to iSwitch1 physically. A physical copper wire inside the FPGA is going to exist, which is pretty neat. So let's do the other signals. We have LEDs 1 through 4 and switches 1 through 4. That's it. We are now done. So give it a name. Switches to LEDs.vhd. .vhd is a VHDL suffix for file types, so that's important. And that's what the first project code looks like. Now let's talk about how to build the FPGA. Now that we have the VHDL and the Verilog done, we're going to be creating the project to build the FPGA. So if you go to New Project, that will open up this box here. Give it a name, Project 1. Sounds good. You do need to select the device. This is the device, the physical FPGA that's on the Go board. So the family is the ICE40, the device is the HX1K, and the package is a VQ100 package. Make sure those are set correctly. And then you also need to set the I/O bank voltage, which are the 4 banks on the FPGA. They're each at 3.3 volts. So everything else is fine. Once you're done with that, click Next. Then add the file that you created from previously, which in my case I put here. So I'm going to do the Verilog one. It's exactly the same for VHDL and Verilog. Switches to LEDs.v. Click this little arrow thingy to put it over here, and then click Finish. And now you will see under Synthesis Tool, Add Synthesis Files, Design Files, there's my Verilog file. So if you double click that, you can see the code that we wrote previously. Note that the IceCube 2 text editor does not have syntax highlighting, so I don't use it for that reason. Then you can double click this right here, which says Run Simplify Pro Synthesis. Now what synthesis does is it actually takes your Verilog or VHDL code and it converts it to physical components on the FPGA. So these are things like wires, physical wires between 2 points. There's things like lookup tables or LUTs, which we haven't gotten into. There's registers, there's blockrams, there's those types of primitive components, which if you don't know what I'm talking about, that's totally fine. We're going to go through them one by one in future projects, and you're going to get a lot more comfortable with them. So if you double click this, I will run through synthesis, which will produce an output, and it will show here some of the usage. This is interesting, and I do want to point this out. So it says resource usage report for switch, the name that you gave it. I gave it switches to LEDs. So it tells you which part it mapped it to, which is this is the part on the Go board, and then it tells you what primitives it actually used. And in this case, it didn't use much. This is a pretty simple project. In this case, we actually use 0 lookup tables, no register bits. So there's not a lot going on here, but we did use some wires to wire up the inputs and the outputs. So that's step 1 of the flow, is synthesis. Step 2 of the flow of building your FPGA is called, the tools say P&R. P&R stands for place and route. So place and route takes the output of synthesis. Synthesis needs to be run first, and it physically puts it on the FPGA. So if you have components like lookup tables and registers, which we don't have it yet, but when you do have them, place and route will actually move those around and find the best spot on the FPGA for those physical components to reside. Now inside the FPGA there are about 1,000 of these lookup tables and registers and a bunch of components. And your code doesn't, you don't tell your code where to put the actual registers, and that's the job of place and route, is it tells it in the output of synthesis where to actually map everything to. Now for place and route to work, you need to give it some constraints. So under add P&R files, you need to give it a constraint file, which in this case we're going to be giving it a pin constraint file. So if you double click on constraint file, this is a little tricky. Under add P&R files, right click on constraint files and click add files. Then you do need to download this file here, Go Board constraints.pcf, which is your pin constraint file. I will provide this file in the notes for this video, so don't worry about it. I will give it to you. So add that there. Now what this file is actually doing, if you look at it, let's open it up. This is the constraints for the Go board. So every single pin on the Go board is mapped to a particular signal name and a particular pin number. So in this case, we have some switches. iSwitch1. iSwitch1 is on pin 53 of the FPGA. iSwitch2 is on pin 51. Without this information, the place and route will still run, but it'll just make up pins. It'll put iSwitch1 on pin 99 or pin 1. It has no idea where to put this signal. So you do need to tell it, listen, this needs to be on pin 53, this needs to be on pin 51, so that it knows what to do with the actual signal. Same thing with the LEDs. There are some other stuff, there's more stuff in here. There's 7 segment outputs, the UART, VGAs, PMODs. There's a lot of information here. Over constraining your design is fine. In this case, we haven't used anything but these 8 signals here, so the tools are just going to ignore these other assignments for now. But we will get to them in a future project. So that's what that looks like. You can close out of there. And then you can, on tool, you can run all, which will run the synthesis again and place and route, or you can just do run to and then click run bitmap. And what this will do is it'll run through place and route and it will generate a bitmap. And the bitmap is a program that generates a bit stream. Now your bit stream file is actually what is being used to program the FPGA. So let's go through that. This will take a little bit of time to go through the place and route, but this design actually is pretty simple. So, oh, look at that, we're already done. You have a bitmap file now. That is the whole purpose of IceCube, is to go through synthesis, place and route, and generate a bitmap for you. Is it worth looking at the place and route report? Probably nothing interesting here. This is probably more interesting for later projects when we actually have clocks, but this does tell you with the output of place and route. There's reports for everything. So there's a report for place and route, there's a report for synthesis. You're welcome to look at it if you would like. I don't think it's critically important. And then here is your bitmap file. So your bit stream switches to LEDs underscore bitmap.bin. And that's the one we're going to be using to actually program the board. So for that, I'm going to open up Diamond Programmer and show you how that works. All right, let's open up Diamond Programmer now. take a look at that. When you first open it up, you're going to be greeted with this Getting Started screen here. So if you plug your Go board into your computer, it should scan for the FTDI chip and it should see this. If you don't see this here, check to make sure that you installed your drivers correctly. So click OK from there. And now what's going to happen is the Diamond Programmer interface opens up, and the very first thing it's going to try to do is it's going to try to scan the Go board. And due to the way the interface is set up, it's not able to scan to see what FPGA you're using, but that's okay. It still works anyway. So it'll give you this error here and it sounds all scary, but don't worry, we're good. So device family, you do need to set this. The family is the ICE40 family on the Go board, and you're using the HX1K, and you want to double click on fast program and set it to SPI flash programming. Erase program verify is fine, and we do want to use the file that we created in IceCube 2. So navigate to where your project is stored and go to SBT outputs bitmap, and then there, the .bin file is what you're looking for here. So we can open up that guy and set the SPI flash. This is the actual flash chip. There's a dedicated flash chip on the Go board, and that's what stores the bit stream that loads the FPGA. So the SPI flash we need to tell the tools about. It is SPI serial made by Micron, M25P10A, 8-pin SOIC. Click OK here. And now at this point I would recommend saving your Diamond Programmer setup so that the next time you close the tool and reopen it, you can just open up these settings without having to punch all that in again. So you can save this, put it somewhere in your project, call it Programmer Config, something like that. Okay. Now you're all set up and ready. Click the arrow program button, green arrow, and it will program the flash. Hopefully the demo works. It did not work. So sometimes this happens where, depending on the computer that you use, it will fail check ID, and it will say it expected 10 and it gets FF. And I think the way to fix that is to go up here and change the port from USB 1 to USB 0. Let's try again. Success. Okay, this is working now. This is interesting. On my laptop, I need to use USB 1. On my desktop, I need to use USB 0. So if you have a problem like I just had there, change your port and give it another go. So now it says operation successful. The Go board is successfully programmed, and you can't see this, but when I push those switches, boy howdy, those LEDs are lighting up. So I'll take another video of that. I'll show you what that looks like. Alright, so the Go board is programmed, and when I push down switch 1, LED 1 lights up, switch 2, switch 3, switch 4. So I would call that a success. Congratulations on your first Go board project. Let's get started with the next one, talking about lookup tables.